Hi everybody, this is Manuel Monetizing, and the subject of today's walkthrough is natural language processing. What we're going to do is attempt to predict what a doctor is going to say next. And that sounds a lot more magical than it really is. We're going to use this concept called Engrams, which is part of natural language processing, to learn a body of text, a specialized body of text on the subject of cardiology. It doesn't have to be cardiology, it doesn't have to be a medical corpus, it could be anything that's specialized. That's what's interesting here. It could be documents, you could learn off documents on engineering, on legal documents, or even, the works of Shakespeare. Anything that's specialized where you want to learn how they would speak, and that's what's interesting. And we're not gonna stop there. We're gonna wrap the entire thing on the Shiny web framework, and this gives us interactive tools to play with the R code. Basically, an input box and a button to predict the next word. So nothing is complicated here. It's just we're stacking a lot of technology on top of each other that it can get complicated, but individually nothing is hard. So as usual, you'll find the code, links, and more information on this walkthrough and others at my blog, and the name should be there in the description and on your screen. And this one is Speak Like a Doctor, Use Natural Language Processing to Predict Medical Words. And I'm going to scroll to, this is what the end product will look like. It's you view it through a web page, but it's calling our R function, so it's really cool. Okay, so I had another walkthrough on the subject of getting medical documents out of PubMed. So I'm not going to talk much about how we're going to do that, because if you're interested in that subject, follow the link and watch that video. Go through the blog on that subject. But basically, it's using the package called RISmed, the library, and we built a function. And that was part of the other walkthrough, and it's very simple to use. We say, get PubMed data, we call the function, and in it we say, you give it the subject. We want documents specifically about cardiology from the years 2013 to 2015, and we want 1,500 documents back. And it's going to query PubMed, which is a large database that contains medical articles, abstracts, quotes, all that good stuff. And you can query it by date, and by subject, by topic. So that's an easy way for us to get a very specialized corpus of text, so we can learn how the world of cardiology talks, speaks, builds their sentences. So actually, you know what? Let's run that while we do it. It does take a little bit of time, and I can talk about Engrams while we're waiting for it to happen. So I'm going to load this in memory. And we're going to call it. And let's fire it up. And this is going to return in the medical underscore corpus variable 1,500 documents on the subject of cardiology. So they're actually abstracts, and maybe each abstract has 10 to 100 sentences on the subject of cardiology. So we'll let it run, and meanwhile we'll talk about Engrams. So Engrams, for those who don't know about it, it's a very typical, highly used method in NLP, natural language processing. So an engram, let's take an example of this sentence. This is my brother. So if you want to say an engram of size 2, you will be basically gathering out of that sentence patterns, two-word patterns, contiguous patterns from the sentence. So you'll end up with 3 engrams. The first one will be this is, the second one will be is my, and the third one will be my brother. As you see, right? It's just pairing it and moving up the sentence, word by word. So in our case, for what we're trying to do, if we had to build the application just on that one sentence, and a user typed the word my and said push the button, says suggest the next word, then of course from what we know we will say, well, we will give the word, we'll suggest the word brother. Well, you put my, and we know that after my comes brother, then here it is. So that's what we're going to do, though we're going to do that for hundreds of thousands of sentences, of pairs, of engrams, you'll see. So let's see how we're doing, if PubMed returned. Yep, PubMed. So we now have 1,500 documents. So let's look at some of them. I'm going to do a head on, and we'll make this bigger. So as you see, it's returning an abstract with all sorts of sentences, and we have 1,500 of those. So what we're going to do here is we're going to break them each out by sentence, and then we're going to get the engrams out of each sentence and build this huge engram library. And that's going to be the engine with which we're going to learn the language or the subject of cardiology. And now that we have our corpus back of 1,500 documents, make this bigger, we're going to move to cleaning this text up. As you see, there's all sorts of different letters, capital letters, lowercase letters, numbers, parentheses. We're going to have to clean that up. So what we're going to do here, I have a function called text to clean sentences. And it's a very simple function, but it's something in NLP you'll always do. You always have to clean your data. You have to learn what it is and then find out exactly what you need and what you don't need. Because if you have too much data, it's going to hurt your models. You just want to have just what you need, nothing more. So in this case, we're going to pass it this entire text blob of data on cardiology, and we're going to use the gsubstitute function. And the first thing we're going to do is this is an important part, we're going to say whenever you find a semicolon, a period, an exclamation point, an interrogation mark, swap it with a character-based code of OOTOO. And then the reason we're doing that is we want to mark the end of each sentence, because that's what we're going to work off of. And then our next call we do, still with gsub, we say remove everything that's not a character. So we only want 26 types of characters and nothing else. So all the numbers are going to drop, all the punctuation, special characters, everything's going to be cleaned out. But we still know where the sentence ends because we swapped each of these this punctuation that normally marks the end of the sentence. We're using the OOTO code. So now we have a text that's completely cleaned out of everything but alphabetic characters. Then we're going to force the entire thing to lowercase using toLower. And we're going to remove words that are we'll change this to words that are between 1 and 2, including 1 and 2. So we don't want is, it, I. We're going to remove all those. That's just going to be noise for our model. So we're going to move them. And finally, we're going to there's also going to be contiguous spaces. We don't want that. That's also going to be more, it's going to just build up some bulk in our vectors and our lists, and we don't want that. So we'll clean them up. We just want one space, never 2, 3, 4 spaces together. And the last thing we do before we return the data is we're going to split this blob by the special code that we did, right? OOTOO, and we're going to return sentences. So cleaned up sentences. And let me just load this in memory. I mean, it's very straightforward. And let me show you how it works. We're now going to pass our medical corpus, right? Medical corpus, which is what we got from PubMed, the medical database, and we're going to have it cleaned. So it's actually called, we're just passing the abstracts. I think we have titles and abstracts. Well, it's easy to find out. Let's see. We have title and abstract, and we just want the abstract. That's the bulk of the text. That's what's interesting. And we're going to clean it up, and this shouldn't take too long. That was pretty fast. And let's do a head on what we got back. So now you see, we have cleaned out sentences. Everything is lowercase, and there's no special characters, and we should have more or less each sentence, right? So how many sentences did it return? Let's see. 22,383 sentences to work with. So we're gonna have a lot more engrams out of those sentences. So it might not feel like a lot, but it's gonna be a lot very soon. And that's exactly what we're gonna do next. We're gonna work on the engram. So the engram, like I said before, it's looking for the patterns in the words by pairing them together. So here's an example. Actually, let's go up here. So this is a big sentence, and we're going to use the library engram. We could very well write our own engrams. It's not complicated. It's just very it's just a pain. If somebody has written a package, and this is a good package because it's very fast to do it, good for us. So if you don't have the engram library, you need to load it. You need to install it, I mean. And let's see. So I'm going to run our test sentence. This is a big sentence through the Engram function from the Engram package. And I'm going to ask for Engrams of 2, right? Size of 2. And let's see what it returns. Oh, no, we need to print a special way to get the Engrams. There, it returned A big. This is big sentence is A. So it's not in the order of the sentence, but really it's a this is one of them, right? Is A is one of them, is A right here. A big is another, and big sentence is another. And if we did, just for interest here, if we ask for Engrams of 3 words, right? So then we get a lot less Engrams back, but now they're triplets. This is A big sentence is A big, right? So these are basically the patterns we're going to use to try to anticipate, to try to predict what is the next word in the sentence. So now we've done this. I'm going to construct again 2 more functions to help us get this done. The first is something I found on Stack Overflow. It's a neat little a trimming function. Surprisingly, R doesn't have a trim function in the base package. So this is just using gsub, and it does it for us. And if you're interested in it, learning more about it, there's a link to where I found it. So we'll load that in memory. And this is a little function I wrote to help us do the Engrams, because we don't want to do just one Engram. We're going to do many of different sizes. So this, all it does is it takes the sentences, the size, the Engram size you want, and it's going to run through each sentence, get the Engram, and return it, right? Get the Engram the right size and return it to us. Basically, it's going to build a huge corpus of Engrams based on the medical text on cardiology. And this is exactly what I'm doing here. And I didn't load that one in memory. I'm going to load it. So here, as you see, we are going to run this multiple times for Engram size of 2, 3, 4, 5. So each time, let's walk through this while we're waiting. So it's going to go through each sentence in the sentences that were returned and cleaned from PubMed. We're going to trim it because we don't want to have, as you may have noticed, there was some spaces at the beginning of some of these sentences. We don't want that. And then we're saying we want to make sure that the sentence is not blank. They shouldn't be, but just in case. And we are also going to make sure the length of the sentence is bigger than the Engram size we want, right? If there's only 4 words in a sentence and one Engram of 5, we need to skip it, right? Because it's not going to help us. We already have that when we did the 4s. And simply we just call the Engram function with the size we want, and we just stack them together. So I'm going to put I'm going to put this on pause a bit because it takes a little time, we're now working on the second Engram of size 3. I'm working off a simple MacBook Air with 8 gigs of RAM, so nothing special there. And I'll be right back. Okay, so they're all done. We've gone through 5 of them, 4 of them, 2, 3, 4, 5 Engrams. And let's see. Now what we're going to do is we're going to stack all of those together into one big list. Okay, so we consolidated everything. Let's see what size we have here. I'll do a length. Okay, so as you saw, we only had 22,000 sentences, and now we have 674,000 Engrams, so quite a big list. So that's good. We want a lot of different combinations so we can accurately predict the next word. So that's good. So one little thing we're going to do is we're going to save this to file. So we're going to save our collection of Engrams to file. Why are we doing that? We don't need it for what we're going to do next, but we're going to need it when we run the Shiny application. Every time you run it, you start it up, you don't want to have to go through the whole process of going to PubMed, getting the medical documents, cleaning them up, running all the Engrams, and then running the application. We just save everything to file, and next time, all you have to do is just run through the Engrams and find the best match for what the word to predict next. So that's why we're doing that, though we're not going to use it immediately. Okay, so here, let's take a peek at some of the words we got. So this is the head of some of the engrams we have. So if you look at the top, we have the pairs, just two words together, right? You know, origin and, patients without, clinical relevance. And if we do the tail, we have the 5 words. So 5 words together for the engrams of size 5s. So that's what we're going to work with. And how many do we have? I forgot already. 674,000 of those. Okay, perfect. So we're going to move on. We have a little bit different size. That's okay. So now we're going to, even though we're going to run this in an application, in a Shiny application, let's run it manually to see how it works. So let me load that up here. So we're going to start with a sentence, this is just one word, the word infection. And we're going to say, you know, predict us what you should say after infection. And you'll notice I'm leaving a blank space here because we're never looking for the end of the engram, right? We always want a space because we always want another word afterwards. That's just a little trick to make sure we never get that last word of the engram. And then we're going to loop through each of these engrams that we have. And we're going to use the grepl function, and we're going to say, find me a match to my word inside your sentence. So, for example, here in this example, if your word was down, you say, find me, do you have the word down in this sentence? And this one would say, yes, we do. We have the word down in this sentence, and it's not the end, right? Because you want at least one space afterwards, right? So this would be a perfect candidate for it. grepl just looks in a sentence and says, is it there, yes or no? And it returns, and this is a way of forcing that it's a beginning of the word. We don't want, you know, if you wanted, I don't know what's, I'm trying to find something here that would, thesis. If you said, I want to find the words thesis, if you didn't put this, you know, this symbology, this collection of symbols at the beginning of word, it would say, yeah, we found the word you're looking for. It wouldn't be thesis, it would be synthesis, right? So we don't want that. So this you know, is just forcing it to say, hey, I want the exact match, at least at the beginning, not at the end, at the beginning. And then we just kind of stack all our matches together. And let's run this to see how this works. And it's actually printing them out. So you see it's finding quite a lot of matches. I guess infection is a very common word in the world of cardiology. And you see, infection, infection, infection. So these are all possibilities. So we have to make a choice, right? We only want to predict one word. We only want to suggest one word. We don't want to suggest 1,000 words. So we're finding this. This is just one assumption I'm making, and it might not be the best, but it's one of them. It's a possibility. I'll make this a little bit bigger. So, you know, this is one. I'm making an assumption here. I'm saying, find me the word. The sentence I want is a sentence with the most characters before my sentence. So we're assuming here, the idea here is that there's a lot of context to the word I'm looking for. So that's the one I want. That's the one I want. So really, there are many different ways of looking at what you think is important, not important. So this is just one approach. So this is going to go through each one of my the matches, and it's going to calculate how much space it has in front of the word. Right? It's going to do this nchar on the split from a match. So we take the sentence, you take the ngram, you find your word, you split that ngram by your word, and you calculate the number of characters before that. So I'll run it again. I think I just ran it, and it's going to return a bunch of numbers, and we're going to pick the biggest number, right? So maybe it'll be 24 here or 30 here, right? Doesn't really matter. It's going to do it for us, and we're going to say, give me the biggest number, and just, you know, if there are many of them, just return one. Basically, give a sample of one. If there's 3 or 4 with the largest number, just, you know, sample one out of there, and let's see what it does. And there it is. So for my prediction of infection, it's going to suggest should, right? Because it has all these words ahead of it, before it. Okay, so that's kind of the idea. Then, so of course, that's the word. Now we need to find, this part is very boring code, right? It's just going to extract the next word after the word I'm looking for. So here we can look at it quickly. It's basically going to split it by the best word, and it's going to say find me the word that's right after that one. So split it. It's going to, so basically what it's doing is it's saying take the best matching n-gram, split it by the word. So again, right, the n-gram, the word I'm looking for, split it. Take the second part this time, right? Take part 2, not part 1 of the split, and split it again by spaces, and just give me the first word you split. So I know it's convoluted, but it works, and it returns should. So that's what we want. So infection should. So that's what we want an application to predict when you enter the word infection. Okay, so that's all really about the application. It's pretty simple. The code is straightforward. I hope you understand it, and if not, it's in the walkthrough. So go there, analyze it. And now this is the fun part. It's building the Shiny app. This is a great addition to R. It's the ability of building a web interface so you can interact with your code. And we're just going to scratch the surface. We're just doing a button, but you can have sliders. You can have a very complicated graphics going on. It's really cool. Okay. So we're going to be using so let me talk a little bit about Shiny, because it's a bit, it requires a few things. So yes, you will need to have Shiny installed. You just do install packages Shiny, and you need to create two separate files. One is called UI.R and one is called server.R. They have to be called that way. There's always a UI layer and a UI layer, right? It's going to be the type of objects you have on your front end, right? If you want button, charts, sliders, text boxes. And as a server is the back end, and it knows how to communicate with each one of these pieces on the front end and pulls the data. So if you ask a request, it's going to read that request, and it's going to get the data and send it back to you. Okay. So, and there really isn't much to look for here. I'm actually going to open it on my machine. I already have them. So let me open UI. So it's basically this code copied here. So put everything, you need to have this file, this UI.R and this server.R in the same folder where we downloaded that CSV with all of our Engrams, right? So put them in the same folder, and that's going to make our lives easier. So Shiny is very simple to use. It has a Shiny UI, and I have some links on walkthroughs and help files on Shiny, so definitely look it up. But basically, in a nutshell, we have a text input box, we want a submit button, and then we want some kind of, the output, a text box where we can put the output. So in our case, the text input is where the user is going to type the sentence, what they're looking for, a suggestion. The submit box is once they've typed their sentence, they can hit submit. And the verbatim text output is where we're going to type the entire sentence plus the suggested word. Okay. And that's one thing. So that's UI.R. Now server.R. There. So we have UI.R, server.R, and let me open this too. So this is the folder that I put. I put Shiny, Speak Like a Doctor. In there I have server.R, UI.R, and all our Engrams, right? That's how I did it. So we went through UI.R. So this is basically, what we have available in the UI. And server is a little bit more complicated, but not that much, because a lot of the code we've already seen, right? We have the trim function, trims spaces from words, from the beginning and the end of words. We're going to use it here too. And then we have code to read all our Engrams, and then it returns data frames, so we're just pulling, we're just creating a vector of the Engrams themselves, so nothing special there. And this is part of the functioning of server, the Shiny server. It has a function, it has input, output, and input is what you pass to it, right? So in our case, it's going to be the sentence the user's typed and wants a suggestion of a next word. So we have database input. It's a function that says find next word. So in this find next word function is going to pass the sentence that was typed, and we pass sentence, and this basically does what we did before. If there's nothing there, if once you've trimmed it is blank, return nothing, and it goes through the matching and the precision match just to return a single word, right? It's exactly the same thing we saw earlier, what we did manually. The difference is this is basically every time you hit the server, it calls this function. This function in return calls the find next word, passing the input value. And every time it's found everything it needs, it assigns it back to the output value and returns it back to the UI. So back and forth, back and forth. And you don't really need to know too much about it. There are great examples about how this works on the Shiny page. There are links in the walkthrough which start maybe with simpler examples and work their way through there. But it's a great tool, especially if you want to build interactivity to your R code. So basically we return back to the UI what the user entered, so however many words they have, and our suggestion, right? So this way it returns a full sentence. It's nicer to see than just that one word. Okay, that's it. So here's the funny part. So you make sure they're saved, and you make sure they're in the same folder as the CSV, what we're going to call. And how you call it is interesting. You need to let's go back here. I have the sample. I have it here. You have to do a call called run app. So you just copy this and you type it directly inside your console window, or in in a standalone console that would work too. And I'm going to put the same path, the exact path of where my files are. If it's going to allow me to copy it, let me just open this here. So I just need a path, so I don't need this. And I'm going to swap it there. Okay, so this is my full path to the folder where I have a UI.R, server.R, and my CSV. And watch, and this is pretty cool. Oh, make sure you don't need to run the server or the UI code, but you do need to load that library in memory. So, and I'll add that to the walkthrough because I think that's an important part. And let's run this again. So run app, path, and there you have it. It opens, it's really cool. It opens a browser window. This is just an option that you can have. You can actually see your UI code and your server code, but you don't have to have it. So I'm going to start with the word myocardial. So, and I hit the button, predict next word. It's going to take a little bit of time. Why? Because the first time you hit that button, it's actually reading the entire CSV and loading it in memory. So we got to give it a little time. There it is. It was actually pretty fast. Myocardial revascularization. You see, that's why we're doing these specialized corpuses, because they'd be hard to come up for, in everyday word, everyday language. Okay, so I'm happy with this. This is what I'm looking for. So what comes next? Hit again. And maybe a little longer when the words are longer, apparently. Or a lot longer. This is one thing I want to talk about too. This code hasn't been optimized at all, so things may be slow, and there's a lot of ways to make it faster. I'll just cover one or two afterwards, but definitely this has not been optimized at all. And you could also have errors too, right? There's a lot of things. If maybe it doesn't find anything, I think it spits out an error. So it keeps on saying, it keeps on building sentences for us. That's what's really cool, right? It's predicting, these sentences which I barely understand. So that's what's cool. So you could do this with engineering documents. If you have access to a big corpus, a couple thousand documents would work. Or you could try all the body of works of Shakespeare, for example. That'd be cool too. So it keeps going. It keeps building sentences. So let's try our infection example again and see if it works the same as we did it manually. So I put the word infection, and let's see what comes up. Infection should, here we'll continue. And while we're waiting, I can show you one area that's very slow here. It's the grepl. This is probably not the best way of doing these matches. You should find more optimized ways. And another thing that would make things faster is using indexes. So instead of using the actual words, use an index. So here it says infection should be, okay. I'm okay with that. And we'll do one more, and then we'll leave it at that. I think you get the gist. But definitely optimizing it to make it run a lot faster, maybe using indexes, and looking at different infections should be considered, blah blah blah. We'll never know because I'm not going to run anymore. But definitely the grepl here, that found out to be one of the bottlenecks of my version of the code. So I think doing a different approach and maybe using indexing the words, so you don't have to carry a huge data set. Basically, every unique word gets a number, and then you would match them that way, because you don't need to match on the word, right? A unique number representing a word would work just as well, and it would be a lot less duplicates that you'd be carrying around. It would be probably a lot faster. Okay, I thought it was fun. I hope you like the Shiny application, and I hope you maybe not for NLP, for whatever you want to do. Check out the Shiny website. There are great tools for interactivity, especially it's really nice with complicated charts, as you can have sliders and change things dynamically. I thought it was really cool. Thank you.